All right, so today we're going to be talking about different types of nuclear particles. So we're going to start by going through our nuclear symbol from way in the beginning of the year. So if you remember, we have our nuclear symbol. We've got our element symbol right here. Okay, and that has to be whatever element we're talking about. Right here, this is going to be our number of protons, also called our atomic number. Okay, and so we look on the periodic table for that, and that's going to have to correlate with this element symbol. From here, we've got our mass number, okay, and that's the number of protons plus neutrons, and that changes depending on the isotope that we have. Over here is where we put our charge usually. We're not going to be worrying about this section right here for our nuclear symbols. What is going to be changing are our mass numbers and our proton numbers, okay? So let's give this a whirl, checking out the 4 different types of nuclear symbols. All right, so we're going to talk about some different types of nuclear particles. Alpha, beta, gamma, and a positron, okay? The alpha, beta, and gamma are all Greek symbols, so these have their special little Greek symbols. So memorize these. This is like a bee with a tail. This is like a twisted Y, and then this is kind of like a fish, right? So the alpha actually stands for a helium particle, so it's going to be 4,2He. You do need to memorize that. And that's going to be our weakest type of particle. It's going to be stopped by a piece of paper, all right? So it's pretty weak. It can be stopped by a piece of paper. Our beta particle is actually another way of saying an electron. So it's going to be 0, -1, and then E, and it's going to be medium strength. This is going to be stopped by like a piece of tin foil. Okay, so that's medium strength. It's going to be stopped by tin foil. And then our gamma particle, okay, that is symbolized in this way. Okay, so it has no mass. It's just energy, and that's going to be the strongest. It actually needs to be stopped by at least an inch of lead. Okay, so that's our strongest particle. So you need to memorize both their strength and the symbol so that we can use them in equations. The positron is kind of like the positive version of an electron, so I think it's important for you guys to memorize this one as well, because we're going to be working with it. Sometimes we have positrons that are emitted in our particle. Okay? And so basically what happens is further down on the periodic table, we've got unstable elements, okay? And they change from one element to another. They're radioactive, some of them, and there's not that much stability in those elements. So there's a lot of mutations. This is basically what happens in the stars, okay? Stars are constantly electrons and gamma rays. Everything is moving around, so we're getting all these different types of elements being made. Okay, so we're going to track how we can see that. Okay, and we're going to do that using a nuclear equation. So this is an example of alpha decay. Okay, so here we've got our protons. Okay, we've got our protons plus our neutrons. Okay, we've got our symbol. And basically we're saying this element, americonium number 95, okay, decays into a helium, which is an alpha particle, alpha, okay, and what? So basically, we're going to use the law of conservation of mass and matter. So there's 95 protons that we start with, so we have to end up with a total of 95 protons. 2 of them are from a helium particle, so how many need to be in this? The other 93. Perfect. So I know there are 93 protons. I look at my periodic table, and I get that the element symbol for this is Np. Okay, now up here, there are 241 total protons and neutrons. 4 of them get split into this alpha particle. So the other ones, 241 minus 4, would be 237, end up here. Okay, and so this is what gets made, gets produced, these 2 things. All right, let's try another one. So this one is phrased a little bit differently. It says, write an equation to show how chromium-51, so this is the isotope, the mass number of chromium, undergoes beta capture. So because it's capture, we know that it starts as in the reactant. Okay, if it's something emits, it goes into the product. So I'm starting with chromium, which is Cr. I I know my mass number is 51, and then I look at my periodic table, and chromium is 24, is its atomic number, all right? So I've got beta capture, so it's going to capture a beta particle. Beta is an electron, so 0, -1 with an electron, okay? And so that is going to produce what? Well, the top part of this is easy, 51 and 0. Start out with 51, have to end up with 51. Easy. This one's a little bit tricky. I've got 24 protons and a -1 proton. So that means that I have 23 protons in my reactant. So I've got to have 23 protons over here. Okay? So you look at your periodic table, and that'll actually be vanadium. And so that's how you need to do that. What I suggest doing, figure out your protons first, then identify what your symbol is, and then figure out your mass number for each. Okay? Let's try another one. All right, we have fluorine 18. Remember, 18 is the number of the isotope, so that's your mass number. And we've got positron emission. Emission means product, so I know that I have to have my positron over here. So I've got 0 plus 1, and then the E. Okay, well, I guess it would be a E plus a little bit. Okay, we'll just scrunch that out. All right, that's being emitted plus what? All right, so we've got fluorine F. My mass number is 18. I look at my periodic table. I know my atomic number for fluorine is 9. So I start out with 9 particles. I've got 1 already, so I know this one has to be 8, which makes us have oxygen as our element. And then I've got 18 in my mass number, so I have to have a total of 18. Well, 0's over here, so it's going to be 18. Okay, so those are my two products, is my positron and my oxygen with the mass number of 18. All right, so those are just some examples of how to do nuclear equations. We're going to do lots of practice in class, but be ready to give it a whirl. All right, nice work.